So you hear me and I can share the screen. Perfect. I heard the same problem happened to someone else earlier today. So all right, good. Then I start sharing my screen. Perfect. All right. Start from the beginning. I hope everything works fine. So I guess, Valeria, you introduced myself. Thank you very much. I'm very excited to be here today to introduce the lithography-based metal manufacturing technology, which is a metal printing technology that is not that much well known throughout the 3D printing environment. So I hope I can share with you how much I do enjoy this technology. Yes, because usually people know powder bed fusion or selective laser sintering or binder jetting. However, lithography-based metal manufacturing is not that widely known. So let's see if I can share the enthusiasm that I have working with this technology. So briefly about myself, I'm the head of application engineering at Incus. After my master's program in Australia and in Germany, and a lot of enthusiasm for 3D printing and new technologies, I decided to join Incus in 2020, and I'm very excited to be part of the team here. About the company itself. So Incus is based in Vienna in Austria and was founded in 2019 as a spin-off of the ceramic additive manufacturer Lithos. And here at Incus, we provide the lithography-based metal manufacturing technology by building the printers, doing R&D to make sure that we are always on top of the technology. And we do the same, of course, for the materials. So we have some of our standard materials, but we still do R&D to have more and more materials. And well, obviously, we do also sell the printers and the materials that come with it, and give all of the input that we can share about all of the post-processing steps and first steps, going from creating a 3D part. We have over 10 machines sold worldwide. Actually, this year we are over 15 machines, and we are a proud member of the AM Ventures portfolio, a big investor in additive manufacturing technologies. The company started as thinking that we want to be complementary to metal injection molding. So a lot of the company was based on that. However, now we are also focusing on production of parts that cannot be formed in any different way. About the technology itself, so lithography-based metal manufacturing, we shorten it up to LMM. It's easier to remember. It's part of metal additive manufacturing. So for those who are not really in metal additive manufacturing, there are two ways of approaching this. There is the direct way and the indirect way. The direct way would be something like selective laser sintering, where we directly shape the metal in the 3D structure that we want to have. And then the indirect technologies that can also be called sinter-based additive manufacturing technologies, they're usually involving a binder system that then needs to be burnt out throughout the further step after printing. And usually it's also powder-based mixed in the binder. So to get the final metallic part, we also need to go through a sintering process. So we densify all of the metal particles together to have the metallic structure that we want to have in the end. How the process works, here is just a little scheme to start with. Afterwards, there's a little video showing how the process works. It's It's similar to stereolithography or SLA that is commonly known in plastic printing, and some people already have it privately at home to play around with. In terms that we do use a photoreactive material, we do have a DLP engine, so a projector that is projecting the structure for each layer of a 3D structure. However, where we are different is that we are, first of all, highly filled with a metal powder, and second of all, that we have a top-down setup. So instead of having the platform going up during the print and printing the other way around, basically, we do print top-down. So the build platform is just going down throughout the print. Why we can do it is that we have a material that is solid at room temperature and that liquefies around 30 to 35 degrees. So we say it's butter-like. So the whole setup is in a cooled chamber. We are around 18 degrees usually, and we have a heated blade that you can see in my screen here normally, that will spread around the solid material, liquefy it, and bring it towards the build area, where during the liquid state, it will react with the light that we are projecting for each layer. And after each layer, also the surrounding material that has not reacted will solidify again and create, therefore, the support structure that we need. So we don't need any contact of the parts onto our build platform, and we can build several parts on top of each other. So we can really do a bigger production also throughout the weekend when no one is around. Yeah, we can build a lot of parts in that way. Also, since we use stereolithography or lithography, a light-based material, we really have one of the best surface qualities and the best details, so we can print really small, really fine structures. I'm always really excited when we get a challenging part and it gets really beautiful after the print already. So I promised a little video. So we will see the heated blade here is moving around, taking the material, spreading it onto the build platform, where then the light is projecting the image for each layer of the part, creating in that way the 3D structure that we want to have. What you see now here is what comes out of the printer. So we have one step that is unusual in 3D printing, maybe similar to binder jetting, because we need to remove everything that's around the parts. In our case, we call it decaking because it really melts away everything that could not react with the light. And this is all done with our HammerLab 35. It's a current desktop plugin produced solution. It's a machine that is roughly 1 meter by 1 meter by 1 meter. It fits perfectly on a lab table, and usually it's a really fast installation. So the customers are usually always surprised that within an hour, once the machine is on the table, we can already start the first print and check that everything is working perfectly. So usually before lunchtime, we are already done with the installation. The build area is limited by our projector. We do concentrate on really small parts. So we have a pixel size of 35 micron. And the build area is about 90 times 56 millimeters in X and Y. Yeah, so it's roughly the size, a little bit bigger than the credit card format. And then in the Z direction, I mentioned we can build, put parts on top of each other. We can go up to 120 millimeters. Then the layer thickness and so on is all determined depending on the material that we use, the powders that we use, and so on. Usually we stay around the 25 to 30 micron for the layer thickness. To overcome the problem that the build platform might be too small for someone, or someone wants to make a bigger production of the parts, we are currently working on our Hammer Pro. It's an upscale of our current solution, and it will have a bigger platform while printing at the same speed. So we will be able to do larger parts. So we will expand a little bit of the applications that we could work with. We will also lower the cost per part, of course, since we can print more parts within the same time. And finally, what takes usually most time in additive manufacturing is the cleaning after the printing. So we will have a semi-automatic cleaning station that will allow us much faster processing of the printed parts. About the material that we can use, I will not go too much into detail. We have, I said, a binder system. I said that we compare ourselves in MIM with MIM. So we use also the same names that we have for the materials. So the binder system and the powder. And then when we combine it, we have a feedstock. So the binder system needs to have a couple of requirements, which is on the one hand that we need to be able to highly load it with powders. We usually aim 55 volume%. Depending on the powder size and the powders, we can go a little bit higher or a little bit lower. Very importantly, to have our self-supporting material, we need to control the solid and liquid transitions. And this is a given. We need to enable a defect-free processing. So we need to make sure that during the printing, there is no issue with the parts, and also during the post-processing, during the debinding and sintering step, everything needs to stay in shape. So I mentioned the decaking. Sorry, first of all, we have the powders as well. We use MIM grade powders, so particle sizes between 5 to 20 micron. We process mainly 316L stainless steel. It's a standard material. We have the most experience with it. It was quite good powder to start with for the first trials. But we also print titanium 6.4, so medical grade titanium, copper or copper alloys, tungsten. We had the possibility to print gold last year, and we will have definitely more possibilities also this year. Cobalt chrome and whatever you can think of, if you have a specific application, it's usually possible to print it with LMM. There was one thing that I wanted to say. Well, I will remember later probably. Yes. So we do not need spherical powders since we mix the powders in our binder system. We can adjust the binder to also be able to process particles that might have rough edges and so on. This is something that is a big advantage compared to other powder bed technologies for metal printing. So here's a little video of the decaking. It's one of my favorite parts of the whole process. It looks always really nice to see the whole material melting away from the printed parts. So you see the block that came out of the machine, and just with the heated fan or hot air blowing onto this block, the parts just come out of it. In the middle of the parts here, it's two parts printed on top of each other, and we can just bring all of this to the cleaning. We have our cleaning solution that we call the Incusol, which allow us to get really the parts clean and get out all the sharp edges and details that we want to see. We have in this slide also a little example of how cool it is not to have any support structures. So this overhang was printed as such in the printer and can then further on also be centered in that way. The debinding and sintering step. So the debinding, we need to concentrate on trying to remove really all of the binder that we have inside. We don't want to have any residues afterwards because they might affect the metallic properties and so on. So progressively we remove and we degrade all the photopolymers that we had in our binder. And then during the sintering, there is a shrinkage happening because of the particles going all together, densifying into a final metallic part. Yeah, so this is a nice example. Here the part doesn't look as sintered. It has, of course, been a little bit polished. A couple of sinter results of some 316L parts that were analyzed by one of our customers and partners, the INSA Institute in Lyon. We have some SEM images. So if you look really into detail, you see all the microstructure of the metallic parts, which is as it should be. The INSA Institute is focused on micro-CT analysis with different machines that they have. They did a nice 3D model of how a part looks with the internal pores, and they found out that we only have 0.27% of pores inside. So we go up to over 99.7 of the theoretical density of the parts of the metal. And we have a carbon content that is within the range that we should have in metal injection molding. And what is really nice, and I don't think I see it with any other metal 3D printing technologies, we have a surface roughness, an RA of 2 micron here. In terms of mechanical properties, I would like to concentrate more on this little table down here. We have the MIM standards written in the bottom, and if we compare it with the samples that the INSA Institute measured, we are always within the same numbers than the standard in metal injection molding. The only thing where we exceed a little bit is elongation, but this is usually adjustable by the different cooling temperatures after the sintering. But in this case, it's really not it's more a positive sign than a negative one. Regarding the applications, as all 3D printing technologies, I could not concentrate on all possible applications. Everything that needs high resolution, small parts, and so on is possible with that technology. This is really something that everyone can see for themselves, but I will go through a couple that we do have a lot. So electronics, smaller, high precision components with high performance and low costs. Ideal with LMM. Here's just an example of a SIM card holder for a mobile phone. Then we have the medical and the dental field. Big focus. I saw that there are a lot of talks about the medical field in this conference. Here we get a lot of requests for small brackets because the brackets need to fit every person's needs and shape and size of teeth. Or we have also, it goes down to having small ear implants. Unfortunately, I don't have a picture in this slide about them. They're really just the size of the tip of a nail. So that is always quite incredible when we get something like this out of the printer. And of course, the pictures that you see here, it's all as sintered, so no post-processing was done. There was no polishing. This is really the surface roughness of RA of 2 micron. People are quite impressed every time we show that. And we had also a polishing company that said that it was so easy to polish our parts up to the point that we can see ourselves in the parts. So that was quite exciting to hear. Finally, since actually not finally, there's another application afterwards. The luxury and watches department is really interested in the technology because we really control a material. Since the powder is directly mixed with the binder system, we don't have loose powders flying around. We really control, it's really a clean process. So when the customer came to print gold, we really had almost no losses. There's here one example that shows the difference between direct metal laser sintering and LMM. You can really see the edges here of the watch case that are not that sharp for the direct metal laser sintering. And with LMM, we have a really nice surface, really sharp edges. Yes, so really nice. And I'm looking forward to work more with the jewelry industry as well. Finally, R&D and tools. This is more an application that is useful for ourselves or other sister companies. We can do anything from little nozzles or fans or or holders for different equipments. And what was really exciting is that we kind of designed our own 3-point bending testing device by printing the parts that were necessary by ourselves. And also a sister company called Opnano asked us to develop one 3-point, so a stamp and a die for their materials because they have really small parts and they cannot find something actively in the shops and so on. So it brings me already to my summary. The advantages of the LMM technology: complex, small to medium parts, a great resolution, one of the highest on the market for metal additive manufacturing. We can process a wide range of materials, whether they are flowable or not. We have a simple and clean production process. We just have a block of material that we can put in the machine if the customer doesn't want to do the mixtures or work with the powders itself. And the cleaning as well of the machine is much easier since we don't have this slurry sticking around. Yes. And one point that is really, that I really like is that we have a safe working environment. I said no metal dust. We do not have a high-powered laser. We have a visible light DLP engine. So very safe on that side as well. And that was it for me. Thank you very much for your attention. I do hope that I could share with you how much I enjoyed this technology and working at Incus. And I'm happy to answer your questions.
Thank you very much, Denise. Very, very interesting. And we have some questions. So we have a few minutes to still reply.
And I can hear you. I'm super happy.
So can you hear me and everything's fine?
Yes.
Perfect. So are you ready for first question? Do you have partners for the sintering process, or can it be done in-house?
So that's a good question. We received a sintering furnace now in-house. We were not able to use it yet, unfortunately. We had some partners who were doing the sintering for us for up to now, but this year we will start to also develop our own curves and do it all in-house.
Okay, so thank you very much. And second question, this is more tricky. I know that a lot of people normally ask, what are the mechanical properties compared to the traditional manufactured metal parts?
Yeah, I have to be honest there. I never compared our mechanical properties to the traditional manufactured part, always compared to MIM, being kind of traditional already. It's been there for a while already. Well, in that case, we are very similar. So I believe we are also very close to the traditional technologies. Of course, we do have a very small amount of rest porosities inside our parts, which slightly affect it maybe. But the final parts can be used in industry as well already.
In industry, yes. Do you have an idea of, for example, the density of the part?
So for the 316L, it's we are over 99.7% of the relative density. So we are very, very good here. And I think by using maybe also some hipping, so the hot isostatic pressing, we could even go to over 99.9 and also be ready for the jewelry industry, which is very picky for the small porosities left. So yeah, we will develop the rest of the materials as well, more into details.
That's great. So have you already tried some surface finishing?
Yes. I did not have them in my slides. And I mentioned that we had this one polisher who was really excited with our parts, and we will have within the next few months probably a LinkedIn post that will show how nice the parts look after the polishing.
Okay, great. So a lot of new things to do and some growth, and I'd like to wish you all the best, because the technology is always very interesting. There are a lot of things to do, and congratulations.
Thank you. I hope that a few people listened in and realized that we are not trying to replace anything. We are just a little plus when it comes to really, really small parts and fine details.
Yes, exactly. Thank you very much. This was very, very interesting.